understand how this worked, but it did. We have it here for each of the steps in our processing, even for the kp-fits file, which have many standardized extensions. So now that's the state of the pipeline. That's the version that's available on GitHub. Now, if you use it, everything really looks like the regular web pipeline if you want to modify steps or run it with custom hooks or things. Still not working quite. OK. And now I just want to use the last few minutes to show a use case that we have for it in geo time. It's a program led by Loic. It's a survey of 20 white dwarfs, so very faint brown dwarfs. Their luminosity peaks around 5 microns. So Webb is the observatory to search for companions around these objects. And here, our goal is to probe very short separations, close to 100 milliarcseconds, search for cold companions. So if the primary is a very cold object, the secondary will be even colder. So that's very exciting, because we're sort of reaching the gap between the coldest brown dwarfs and Jupiter, basically. Click here, OK. And this led to the discovery of the first Y plus Y dwarf binary. Now, this analysis was made by our colleagues in Michigan with an empirical PSF modeling pipeline. So you can also detect these types of companions with empirical PSF modeling, and that's what's shown here. So the primary is around maybe 15 Jupiter masses, somewhere between 11 and 18, and the secondary between 8 and 28, and 5 and 11 for the secondary. So yeah, that's the system that we have detected a companion in with empirical PSF fitting. And we also tried with kernel phase right after, and it also worked. So if there was no companion here, you'd expect a straight line. Now we have a very clear signal here. And when we fit for this, we actually detect the same companion. So with the same parameter, the blue shaded regions are empirical PSF results. And the dotted red line in the histograms are from kernel phase. So kernel phase gives slightly better precision based on this, but we're still working to understand really the systematics to make sure like which techniques actually gives the best and most precise results. So I'm hard at work on this right now.
Sorry,
yep. Yeah, okay. So if there was no companion, you'd expect all the error bars to basically overlap pretty much with the dotted line in the middle, because you'd have 0 for the whole thing. And now you have very clear excursions from 0. They're not supposed to look intuitive or anything. You're just supposed to see that you have strong discrepancies from 0. And if you revert that back to image plane, then it's very clear that it's a companion. But yeah, it's an unintuitive space to work in, but there's something there. And we can also derive detection limits based on this. Right now, we're reaching 6 mags at about 200 milliarcseconds. That's not as good as we were hoping for. I'm still working also related to the calibration and systematics. We're hoping to improve the detection limits as well. But you can already do very interesting science with these types of results, as we've just seen before. And yeah, next we're working, there's also a 1/f noise correction that Loic made that we're applying to this data right before the kernel phase pipeline. So we're working on exploring the impact of 1/f noise correction. So I'm very interested to see what people are doing for this here. Same thing for charge migration, which we suspect might be causing issues, especially when we're taking Fourier transform and we have these very strong differences. And then, yeah, trying to calibrate and understand systematics. And once that's done, compare with empirical PSF modeling to really see which technique will give the best results in the future for this type of work with Webb. And also, I'd like to see if there's a way to get a closer synergy with the Webb pipeline, in particular for aperture masking, because a lot of the steps I described are also useful for aperture masking, I think, where you apply the same type of processing, but for a different type of observation. And on that, I'll leave my summary. Thank you.
All right, well, we have a couple minutes for questions, so I guess I will ask the question, how does this technique compare with ground-based near-infrared interferometry and AO capabilities? Really cool technique, by the way. So not aggressive question, just curious.
Oh, sure. Yeah, I guess it doesn't reach as high, as small separations as you would with ground-based interferometry, because if we're talking about long baseline, because obviously you have dozens of meters between your telescopes. But to search, for example, with gravity, you really need to know the position or to have a small field of view. So to systematically search for companions, this might work better. And also just the type of stars that we're looking at. So for white dwarfs, we can't access them with ground-based telescopes for this type of work. So that's one example where I think it's to our advantage. Yeah. Thank you.
I found another way. Just that this works.
Yeah. No. Yeah. Okay. Hello, can you hear me? Yes. Okay, my name is Maria Gabriela Navarro. I'm a postdoc in Rome. I don't know why it's okay. So yeah, I brought a similar problem that Gabriel just shown before. We are studying H846, which is a protostar. The main idea is that it's a very bright protostar with some ejection and accretion processes that are showing these very big structures like the collimated jet with this an atomic jet, and then the winds that are creating the cavity around, which is emitting in molecular lines. So we are observing this object near the source, and we are facing multiple problems now with the pipeline, so we try to fix them outside the pipeline. Actually, we were talking with some people from here because we faced some of the issues that still they are not solved, so I will show you now. So we observed with MIRI and NIRSPEC, and we did some mosaics around the central part of the H846. One of the problems that we face is the one pixel problem. So this is, these are the pixels you see in the left side that we got from the one frame from the mask. This is NIRSPEC, but we have the same problem with MIRI. So there you can see that it's pretty clear that these pixels are not part of the emission of the source, and they show the Dieter pattern, and also in this case it's a 4 mosaic, so you can see the 4 parts here. The problem is that we cannot solve this with a normal sigma clipping because the emission is similar to the source one. So it was pretty difficult to deal with them. So for MIRI, it worked with the cosmic. So it's pretty simple. We ran the cosmic to all the MIRI data of the mosaics, and then we updated the DQ mask before running the step 3. But with NIRSPEC, we had some problems because the cosmic was not working well, and actually we had to produce some analysis which is similar what Gabriel mentioned before, that was just checking the pixel itself in all the frames and see how different they were according to the next pixels around. The problem was that since I'm working with other projects, this method is not working in all the data set with the similar objects. So I'm bringing more a problem than a solution because I really don't know how to fix it. In this case, it works, but in some other cases, it's not working well. And another thing that also is pretty difficult to solve now is the continuous subtraction, because you can see there that the source is pretty strong in the infrared. So this is the MIRI mosaic. And yeah, the emission is pretty strong in the center. And actually, this is the interesting region that we want to observe. So for doing the continuous subtraction, we tried different methods. And we faced the fringing problem. Even if we were applying the fringing correction in both steps in the pipeline, We try to fix it, and still we don't fix it to 100%. So for example, we did the normal continuum fit subtraction, which is what you see here, but we tried other methods. For example, we were finding peaks in the specific pixels of every spectrum of all the mosaics, and we find the peak, and then we mask it, and we subtract everything, so we got just the line very clear here. But around the SERS, we always have some problems, and still we cannot do all the analysis we want to do until the very center. We try to mitigate the fringing, trying to use, for example, all the pixels around each pixel, and this would reduce the fringe pattern. But still, in the central part, we are not sure if we can trust the data we have and the results we have, for example, for the temperature and everything. So if you have any suggestion, maybe you can come to my poster if I find my luggage because it was lost. But yeah, I'm interested to know if you already know how to solve this. Thank you.
So keeping up with the schedule changes here, we have one more poster, is that right? Right now? One more in-person poster. And then we'll have Ian giving a remote talk, and then we'll have Bernie's talk. And then we'll have
Yes. All right. This should be on. Yeah, okay. Hello everyone, I'm Dries van der Putte. I work here at Space Telescope as a postdoc. And for the past 2 years or so, I've been involved with the PDRs for All ERS program for JWST. So this program observed the Orion bar, which is a photodissociation region excited by the trapezium cluster. So, and the program consisted of imaging and then mosaics of near-spec and MIRI IFU. So because the Orion bar is really bright, these data had a very high signal to noise, and they turned out to be quite useful to discover some things about the calibration with the early JWST pipeline. Today I'm mostly going to be showing some things that I've seen in the spectroscopy data. So what does spectroscopy data look like? Well, I've extracted a spectrum here from like a little square over there. So this is in the atomic region of the PDR. And we can just look at the entire thing here. So this is very nice. And I just want to highlight here that when we first got this data, there were big jumps between the different spectral orders. But with the latest calibration, this is actually only minor. So in the beginning, we tried to develop all kinds of things, like do we multiply it? Do we give it an offset? Do we give the spectral segments some kind of slope? But now, like, most of those worries are mostly solved by updates in the pipeline. I also want to talk about a pipeline script that we made. So because this is an ERS program, so during the early phases of the JWST pipeline, there were frequent updates, constantly things that changed, and we frequently re-reduced the data. To do this in a more consistent way, we just made a simple script that drives the pipeline. So it's in Python, and it just calls the steps individually. It's not released yet, but I found this quite useful not only for these data, but as a good starting point for data in general. One little quirk here is that it generates its own association files, because there were also some problems with the association files in the beginning. You basically just sort your files into science files, background files, and also the near-spec leak calibration imprints. And then the script will gather all these files, make association files for you out of them, and then run them. And it also works in parallel. And then a couple of corrections I want to talk about. On the left, so these are some plots that are on my poster. the left plot shows what the effects of the leak, the NIRSpec leak calibration are, and it's important to do this in a correct way. You can see here with the blue line that there's a whole bunch of basically fake lines that appear in the spectrum, so it's borderline unusable for certain segments. And then we also did a 1/f correction, and then you can see that the continuum, so the red line, you can see the difference here. Yeah, the continuum becomes more consistent. Spatially, you get these annoying bright spots, but if you have a good leak cal, you can just subtract those off. This all works great. So I want to advocate for very conservative leak cal where you do it per dither position. And then a final thing I want to highlight is that we were having some trouble with fringing with MIRI. And for this, eventually, we developed a little bit of our own method. So we downloaded data of a calibration star. We had a theoretical model for the calibration star, and then looked at how the ratio of observation versus theory went. So that's the green line over there. And then by dividing our spectra with these wiggles and like rescaling the wiggles, it was all a bit manual, but we were able to like improve the fringing a little bit more than the default tools. Thank you.
Jan, can you take over from your side?
Yeah, I'm turning on my sharing now.
If this is anything like the other JWST solar system talks I've seen, it's going to be good.
Can you hear me?
We can hear you, but we cannot see
Okay.
yet your screen.
Yeah, it's asking me to quit and reopen BlueJeans, so sorry.
Well, do it as fast as you can, please.
Yes. All right, can you see me again?
We see you. We need to share the
Okay.
screen.
Yes.
Yep.
Right.
Right.
All right, sorry about the hiccup there. So in this presentation, I'm going to cover a kind of a novel method that we've been devising on the Solar System GTO team to really maximize the signal to noise of spectral extraction for specifically NIRSpec and MIRI IFU observations. So first off, I want to cover sort of just the basics of point source flux extraction. So there are kind of two schools of thought. There's the standard circular aperture extraction method, which is indeed the default methodology used in the default JWST pipeline. So there are a lot of advantages to this method. It's very straightforward to implement. There's a lot of available Python packages like FOATutils that handles this very, very simplistically. It's also very fast and readily parametrizable. So the user can customize the aperture size, the annular background region, and play around with different settings very easily. Now, some of the disadvantages is that when extracting within a circular aperture, the pixel noise within the aperture is additive. So the different contributions from all the pixels add up. And for faint sources, this can actually imprint a significant noise contribution to your extracted flux. Another important disadvantage is that this method is highly susceptible to hot pixels and other outlier effects. one can mask these outliers, but the flux is very difficult to retrieve in most of the standard applications of circular aperture extraction. So the other method that people have been using for source extraction is called PSF fitting, or sometimes called optimal aperture extraction. This is essentially using a model, either an empirical model or a functional form, to extract and fit for the flux of the source. So the advantages of this method is that it yields significant improvements to the signal to noise, as well as allows you to interpolate across masked outlier pixels to retrieve essentially the flux in those pixels. Now, this requires a very good PSF model to generate reliable flux measurements. As many of you know, JWST PSFs have a very complex shape that are not very reproducible by simple functional forms like Gaussians or Lorentzians. A lot of work has been put to modeling, both using pre-launch and in-flight data, the PSF shapes of various instruments, primarily focusing on the imaging modes. The current Web PSF package does allow you to generate NIRSpec and MIRI PSFs for use in IFU PSF fitting. However, they do not yet fully account for the detector effects. So in practice, a lot of the real PSFs are not well matched by the current Web PSF models. Another challenge of using Web PSF is that one needs to oversample and resample to align the model PSF with the true source. And this imprints a lot of numerical artifacts and can be very significant for faint sources. This is, of course, a very dynamic problem that's continuing to be improved. In fact, there is a calibration proposal in cycle 2, I'm a co-ion, that is going out to improve our understanding of the NIRSpec IFU point spread function. So look forward to improvements to a PSF in the coming years. So the method that we've devised using a lot of the NIRSpec GTO data is really to take advantage of the full stack of wavelength slices within the IFU cubes. Essentially what we're doing is we're leveraging adjacent wavelength slices around a given image that we're interested in to empirically create a self-consistent PSF model that is then used to fit the source within the central image. This folds into all the 2D effects across the dispersed image on the NRS 1 and 2 detectors, as well as handles self-consistently subpixel centroid drifts. So there's no need to fit for the centroid. By using the data itself, essentially modeling the scene using adjacent wavelength slices, we are naturally folding in all these effects. And this has really given us a huge leg up on extracting very high signal to noise spectra for faint targets. This method also is self-contained in the sense that it is robust to changing instrument performance. For example, if flat fields and other detector effects are variable, as we've seen throughout cycle 1, there's no need to update external models, but since we're using the data itself as the PSF model source, we're able to subsume these changing effects within the PSF modeling. So let's talk about the kind of a high-level overview of this method. So the starting point of the PSF fitting is the S3D files, the level 2's S3 or level 3's S3D files. So prior to this, there are a number of steps that we do that have been discussed in other presentations, such as global outlier flagging, as well as read noise correction, the 1/F correction, using techniques such as NS-clean. For MIRI, whenever there's a dedicated background, that background subtraction is done prior to this step. So we have background subtracted images in the cube. So the beginning of the PSF fitting, for a given image n within the cube, we define extraction background regions. So the extraction region is a central region centered on the brightest pixel of the source, within which we are actually measuring the flux. And then there is an outer background region defined by an inner bounding box shown in yellow in the figure in the bottom left, beyond which we are sampling the background, any residual background in the image. Now we found that placing the extraction region relatively close to the peak of the PSF yields significant improvements to the signal to noise over wider apertures. And this is because by modeling the PSF flux using more of the high signal to noise pixels, we are less sensitive to some of the low level variations that will otherwise contribute a lot of noise to the extraction. All right, so the kind of the key, hello? Did someone say something?
You go ahead.
You're fine.
Sorry?
Just continue.
Oh.
You're absolutely fine. No problems.
Okay, I heard somebody say something. Okay, sorry. Yeah, so the main step is step 2, where we are taking a moving window of half width k slices and essentially doing a collapse median of the source after subtracting the background. This creates a template PSF that is then fit to the image n that we're interested in, and this template is normalized to a unit sum of unity prior to the fitting, so that the amplitude that we fit for is indeed what we take to be the extracted flux of that image slice. And here in the bottom right, you see an example of the residuals that left over from this method, and we see that this is indeed, unsurprisingly, a very good fit of the PSF, because we are specifically using the local PSF shape from adjacent wavelength slices. All right, so let's kind of dive into some of the highlights from applying this method. So this is a GTO observation of the large KBO gong gong, so V of 21.4 mag during this epoch. And in gray here in the background, we see what we get from the pipeline default. It's a circular aperture extraction. And you see that it's significantly noisier than the PSF fitting result in blue. And some of the science that we were able to get only with this PSF fitting method can be seen between 3.3 and 3.5, where this PSF fitting method retrieves the individual absorption bands of ethane ice, otherwise obscured in the standard circular aperture extraction. Also, spectacularly, at 4.25 microns, we're able to resolve the CO2 ice absorption. This is a nu3 vibrational band that is completely undetectable in the circular aperture extraction. And this is extremely important for understanding the volatile ice compositions of these bodies. Pluto, probably one of the most well-known of the KBOs, was observed on 4 different occasions during the GTO program in 1191 to cover the entire surface of the body. And the spectra are spectacular. They show a huge range of absorption features. At short wavelengths, we see a lot of methane lines, and the additional SNR that we get from the PSF fitting is really allowing us to measure band depths and centers extremely precisely. Now, perhaps one of the most surprising or exciting observations that we got from this data set is highlighted